Hello friends, I'm Sarita and I'm your Gyaani Buddy for today. And today we are going to look at Lp4 SEOA Assignment 1 Fuzzy Sets. So the video is going to be divided into three parts. First one is the prerequisites, where I will explain some concepts related to theory, some definitions with the help of some examples. Second one is the code and its explanation. And third one is the Fiverr questions that may be asked during your practical. So let's look at some of the basics. We already are familiar with the set data structure. So a regular set or a crisp set is a collection of unique elements. So we have already learned this in previous classes. So to understand what a fuzzy set is, let's understand the meaning of word fuzzy logic. So let me take an example. Let's say I want to create a set of funny people or people having good sense of humor. So when I say that some person has a good sense of humor, or he's the most funniest person that I know, then it doesn't mean that other people are also going to find them funny. So this description that someone has a good sense of humor is not very clear. It is vague. That is exactly what fuzzy logic means. It is not 0 and 1. Not everybody is going to think the person is funny. Some people may or may not find them funny. So basically, this kind of description, this kind of measure of uh, funniness, I guess, is vague or it is not clear. This is called as fuzzy logic. So in a set, when I select some people uh, who I think are funny, they are not going to be equally funny. So if I try to rate them based on their sense of humor between, let's say, 0 to 10, I'm not going to score everyone 10. I'm going to give them marks like 5, 6, 7, 8, whatever. So basically, they have different measure or different amount of sense of humor in them. I guess that's what I'm trying to say. And this is basically exactly how a fuzzy set works. A fuzzy set will contain the elements, but they will have different degrees of memberships. So imagine the membership is the measure of sense of humor. So if I rate some element, if I rate some person uh, 7 out of 10, then their degree of membership will be 0.7. Similarly, if I find someone is boring and they are not funny at all, and if I rate them 2 out of 10, then their degree of membership will be 0.2. That is, they can be in the set, but they are only zero point 0.2, but the degree of their humor is only 0.2. That's what I'm trying to say. So this is basically how you can define a fuzzy set. Fuzzy set is a set having partial membership between 1 and 0. And this degree of membership that I keep talking about is defined by a membership function. So, to discuss these concepts in more detail, let's go to the whiteboard.
Okay, let's look at the example now. Let's say this is a class of 100 students and I have selected two people to be in my fuzzy set. This is A and this is B. Well, I have rated A to be 0.6 degree of funny and I have rated B at 0.8 degree of funny. Now, these two become a fuzzy set S and this class of 100 students, as explained before, becomes the universal set U. Now, how are we going to denote S? S is denoted as the collection of ordered pairs. You will be using S as we write the presence of element A along with its degree of membership 0.6. Similarly, B, 0.8. Bracket closed. That is how you represent a fuzzy set. The mathematical notation for the same is as follows. Bracket open, and then you write ordered pair of element E and its membership function of the element and bracket closed. For all such elements, belonging to. That is how we denote a fuzzy set. Okay, so now let's look at the membership function. We will define the membership function. It is denoted using Greek character mu. You write it in the following way: mu, name of the fuzzy set, let's say A, and the element. It takes the value between 0 and 1. This is how we represent a membership function of a fuzzy set element.
To revise once, membership function is basically a function which gives the degree of membership of an element which is present in a fuzzy set. Fuzzy set is denoted as follows. This notation is very important with respect to your practicals. You can say that fuzzy set is a collection of ordered pairs where each element is accompanied by its degree of membership. Now let's revise the differences between crisp set and fuzzy set. So as we have seen, in a crisp set, an element is either a part of that set or it is not. So we can say that the membership function will only give out two values, either 1 or 0. But in case of fuzzy sets, it can give any values between the range 0 and 1. So we can say in a crisp set, logic is only by value, whereas in fuzzy set, logic is infinite value. In a crisp set, membership is precise, whereas in fuzzy set, membership is vague, it is partial. Crisp sets can be used in digital designs, whereas fuzzy sets can be used in fuzzy controllers. We will look into the applications of fuzzy set in detail later. Now let's look at the fuzzy set operations on the whiteboard.
Okay, so now let's look at the union operation of fuzzy sets. Usually, on normal sets, we simply take all the elements of set A and all the elements of set B, A and all the elements of set B, and put them together in a set which is the union of these two sets. But in case of fuzzy sets, we have to also think about the membership function because no element is completely a part of that set. So we cannot simply add those elements in the union. So to deal with this to degree of membership function, remember this formula. Mu of A union B. Mu represents the membership function for an element X, let's say, is maximum of mu of A of X and mu of B of X. Let's write the union of A union B. Now first we consider element A, and for its membership we compare the degree of membership of the set A and set B. Here it is zero point 0.6 and in B it is 0.3. We have to select the maximum of the two. So we simply compare these two degrees and get zero point 0.6, which is the membership degree of A. Similarly, for B, we compare the degrees of membership zero point 0.1 and zero point 0.4. Since zero point 0.4 is larger, we select zero point 0.4. Similarly, for C, zero point 0.9 is greater than zero point 0.5, and for D, zero point 0.6 is greater than zero point 0.4. So this is how we get the union of two fuzzy sets. Union of a fuzzy set is also represented as an or and operator. Okay. So as we have learned the union operation, let's now look at the intersection operation. Now let's look at the intersection of A and B. Okay, here, normally we simply select the elements which are present in both the sets. But here we have to already consider the degree of membership of that element. So, so deal with that. We have a formula mu of A intersection B is equal to for particular element is equal to minimum of mu of A of x, comma mu of B of x. So previously in the union operation we select the maximum of the two, and here in the intersection operation we select the minimum. Let's calculate the intersection for set A and set B. A intersection B is, is given by for element A. Let's compare the degrees of membership, which is zero point 0.6 and zero point 0.3. As zero point 0.3 is less than zero point 0.6, we select zero point 0.3. Similarly, for B, zero point 0.1 and zero point 0.4. As zero point 0.1 is minimum, we select zero point 0.1. Similarly, for C, as zero point 0.5 is less than zero point 0.9, we select zero point 0.5. And the same for D, as zero point 0.4 is less than zero point 0.6, we select zero point 0.4. And this is the intersection of set A and set B. So now, as we have looked at the intersection of set A and B, let's move on to the complement operation. Usually, for normal sets, a complement of a set is basically contains all the elements which is not present in that set, right? So, here also the concept is similar, but we have to perform the operation on the membership function. So, in case of normal sets, complement of a set includes all the elements which are not present in that particular set. But same again, in case of fuzzy sets, we have to consider the degrees of membership. So, we have to perform the complement operation on the degree of membership itself. So, so the formula is as follows. A of x is given by 1 minus mu of A of x. We know that the degree of membership only ranges between 0 and 1. So, when we subtract the degree of membership from 1, we get a complement of that particular degree of membership. Let's calculate the complement of set A. Complement of set A is A, comma. Now we have to perform operation on degree of membership. 1 minus mu of A, which is 1 minus zero point 0.6. Basically means A, comma 0.4. Similarly, we can calculate the same for all other elements B, comma 1 minus 0.1, which is 1 B, comma zero point 0.9, C, comma 1 minus 0.9, which is C, comma 0.1, and D, comma 1 minus 0.6, sorry, 1 minus 0.4, which gives D, comma 0.6. So this is the complement of set A. Okay. So in case of normal sets, we write the difference operation as A minus B equals A intersection complement of B. So if I have to represent it using a diagram, let's say this is set A and this is set B. This is the area which you get in difference operation. So now let's talk about fuzzy sets. Again, we have to operate on the example given above. Mu of A minus B bracket of x equal to mu of A of x, comma 1 minus mu of B of x. Like in normal sets, we perform intersection on A and complement of B. Similarly, for intersection, as we take the minimum choice, we take the minimum of these two values. So you can remember it in this way. We take A intersection complement of B. Similarly here, we take minimum of mu of A of x, comma 1 minus mu of B of x, which is the complement of P. So now let's perform the difference operation on the given example. So A minus B, for element A, we take minimum of 0.6, comma 1 minus 0.3, which is 0.7. We take 0.6. For B, we take minimum of 0.1 and 0.4. Oh, 0.1 and 1 minus 0.4, which is 0.6. We get 0.1. For C, we take minimum of 0.9 and zero point 0.5, which is 0.5. For D, minimum of zero point 0.4 and zero point 0.6, 1 minus zero point 0.6, which is 0.4. So we take zero point 0.4. So the final set 1 minus B is equal to is as follows: A, comma 0.6, B, comma 0.1, C, comma 0.5, and D, comma 0.4. So this is the difference operation.
So now we have covered 4 fuzzy set operations. Now let's look at the fifth operation, Cartesian product. To understand this operation, we need to understand the concept of fuzzy relations first. A fuzzy relation generalizes the degree of membership grades. Okay, that's a bit hard to understand. I will explain. Membership grade indicates strength of the present relation between elements of a tuple. Back to the whiteboard.
So now that we have understood the concept of fuzzy relation, let's try to get Cartesian product of the given example. Here, to get an n-dimensional array, we need to perform some sort of operation of on both these membership functions. The formula for which is given by for element x comma y is equal to minimum of mu of a of x comma mu of b of y, where for all x belonging to x and y belonging to y, where basically x are members of set A and y are members of set B. Cartesian product of A and B is equal to. Now we compare the element A with all the elements in set B. So let's compare the degree of membership, zero point 0.6 and zero point 0.3. Here we have to choose the minimum. So obviously 0 point 0.3 is the minimum. Now we compare A with second element in set B, which has degree of membership 0 point 0.4. So here we select 0 point 0.4. Now we compare it to the third element, which is 0 point 0.5. We select 0 point 0.5. Now and finally element D, which is 0 point 0.6. Since both of these are equal, 0 point 0.6 is the default choice. Now let's do the same with second value in set A. So we have to compare the degree of membership with all the elements in set B. 0 point 1, 0 point 0.3 is 0 point 0.1, 0 point 1, 0 point 0.4 is 0 point 0.1, 0 point 1, 0 point 0.5 is 0 point 0.1, and 0 point 1, 0 point 0.6 is 0 point 0.1. Similarly, we carry on the same operation for element C and D. 0.9, 0.5, 0.9, 0.4, 0.9, 0.5, 0.9, 0.6, and for D, 0.4, 0.3, 0.4, 0.4, 0.4, 0.5, 0.4, 0.6. This is the Cartesian product for the given example. I hope you have understood this concept. Now let's move on to the max-min composition. Before taking a look at the max-min formula, let's look at the presentation first. So, to revise, composition is basically merging two different relations. Now, we don't need A and B set. We need two fuzzy Cartesian products or two different fuzzy relations. Let's take two values. Okay, so now we are back. We have two fuzzy relations R and S as follows. So, how to calculate max-min composition? As it is said in the name, as it is already given on the name, first we take maximum and then we perform minimum operation. First thing, degree of membership U of x comma y and mu of y comma z. This is the formula for max-min composition. So what is mu of xy and mu of yz? We already know that R and S are two fuzzy relations of two compatible fuzzy relations of on two different Cartesian spaces. R is on xy and S is on yz. The max-min composition that we get from R and S is on Cartesian space x comma z, which is why mu of x comma y and mu of y comma z, bracket close. This is the formula for max-min composition. Let's try to solve this problem for R and S. R dot S is equal to, here the minimum, let's go step by step. Minimum of mu of xy comma mu of yz. What is mu of xy? Xy are the position or the points which specify the position of a particular element. So mu of xy is 0.3, first element, and mu of yz is 0.9, first element. So we have to select minimum of 0.3 and 0.9, which is 0.3. And again, we have to, this is only the one element. How can we perform max operation on this? So we continue to go row wise in R. So here after 0.3 we go to 0.6, and after 0.9 we go to 0.5. So now we compare 0.6 and 0.5. 0.6 and 0.5, which is minimum, obviously 0.5. So now that we have a tuple here, we perform the max operation on this tuple, which is basically 0.5. This is the first element in ROS composition. Similarly, we do the same thing for the second element. Now, similarly, we perform the same process for second element now. So, first row in R and second column in S. So, let's compare 0.3 and 0.1. Which one is minimum? 0.1. Now let's compare 0.6 and 0.7. Let's compare first row in R and second column in S. So 0.3, first element is 0.3 in R and 0.1 from S. So the minimum of these two is 0.1. Second element is 0.6 and here it is 0.7. So the minimum element is 0.6. We have to choose the maximum of these two, which is 0.6. Similarly, this is the second element for our composition. Similarly, we perform this on the next row. Now we perform it on row 2 of R and column 1 of S. So let's look at 0.2 and 0.9. Minimum is 0.2. Then we select 0.2. 0.8 and 0.5. We select 0.5. And we select the maximum out of this, which is 0.5. Let's compare now 0.2 and 0.1. 0.1 is minimum. Now between 0.8 and 0.7, 0.7 is minimum. So now we select maximum out of these two, which is 0.7. So this is the max-min composition. Now let me present it in a proper form. ROS is given as 0.5 first element, then zero point 0.6 the second element, 0.5 and 0.7. This is the max-min composition of the relations R and S. Now, let's get back to the presentation.
So now let's look at the implementation of all these 6 functions. So here I have initialized set A and B with 4 elements which are going to be used as input for all 6 functions. Let's define union operation. As discussed before, union operation basically selects the one which has higher degree of membership. So let's initialize the output set C, iterate through all the elements in A, and here we will check which of the element has higher degree of membership and assign it to C. So if A of I is greater than B of I, then C of I is equal to A of I. Else, if B is greater than A, then C of I is equal to B of I. Once we iterate through all the elements, we can simply return set C or we can print set C. That's it. Let's once call this function and check the implementation. So here we can see the union. For A1, we have selected the maximum value of the two, which is 0.9. For A2, 0.7. For A3, 0.5, which is the same. And for A4, it is 0.6. So the union operation is basically working. Now, let's write the code for intersection. Oh, okay. Intersection. Again, pass A and B as parameters. Here we have to select the element which has lower degree of membership. So basically the code will remain same, only the condition will change. Iterate through all the elements in A. Here the condition will be different. If A of I is less than B of I, we have to select the minimum. So I is equal to A of I. And otherwise D of I is equal to B of I. Once we iterate through all the elements, again we can simply print intersection and output D. Let's call this function once. Intersection A comma B and see the results. Here again, we can see that for A1, it has chosen the minimum value 0.3. For A2, it is 0.4. For A3, it is 0.5. And for A4, it is 0.3 again. So this function is working. Now let's look at the complement function. Define complement. And here we only have to pass one element. So let's initialize output set E, iterate through all the elements in set A. And in a complement, we are basically subtracting the degree of membership from 1. So E of I is equal to 1 minus A of I. That's it. Now we simply print E and check the output. Complement of set A. So here we should get 0.7, 0.6, 0.5 and 0.4. It is 0.7, 0.6, 0.5 and 0.4. So complement function is working properly. Let's now write the difference function. Definition: difference, pass the sets A and B, initialize the output set F, iterate through all the variables in A, and here again, as we have seen before, f of I is equal to, we select the minimum, so we use the minimum function of A of I and complement of B of I. So it means 1 minus B of I. So after performing this, we can simply print f. Okay, ही line परत घेते हैं. So after iterating through all the elements, we can simply print f and check the results. Difference A and P. Oh, so to deal with this issue, we can simply write ROU. Oh, okay. So now here you can see that the decimal values are a bit too long. So to restrict these values, we can simply add another function here, as you can see in this line, round. Round will basically limit the values, the decimal values up to 2 places, or we can specify it to be up to 1 place as well. But 2 works just fine. See, now they are properly initialized, and we can see the difference between A1, A2, A3, and A4. So now let's look at the Cartesian product implementation. Cartesian product P. We know that a fuzzy relation is an n-dimensional membership array. Here n is equal to 2. So we will initialize R as a 2D array. We'll initialize empty lists R I in range of length of A. So since A and B both have equal elements, 4 elements each, we will initialize R with 4 empty lists, list of 4 empty lists. Let's start the function I is equal to 0, initializing for, let's say, X in A and for Y in B, we write R of I dot append. So basically we are appending an element in the first place. That's why we are selecting first element. Oh, okay. कट करते लास्ट लाइन कट कर त्याचं काही मीनिंगच नाही परत पहिल्यापासून so let's initialize R of I append minimum of A of X and P of Y. Here you can take other functions as well. Instead of writing minimum of A and B, we can also write minimum of complement of A and B, which will, in a sense, will be maximum of A and B. So you can select some different functions as well. Let's increment the I plus 1. Okay. Now, once we have done that, once we have iterated through all the elements, we will simply print relation I. Now let's initialize another fuzzy relation with the complement pattern so that it will become more clear. R and S. And here, instead of A of X, we write 1 minus A of X, and B of Y, we write 1 minus B of Y. So we are basically taking maximum, but we can write it in this way as well. Print S. Okay, so this is the function for Cartesian product, and we have already uh, created two fuzzy relations. Now let's check the output. Cart product, comma p. Okay, so I haven't written in here. So guys, I made a mistake earlier. So this increment operation should be done in the outer for loop and not in the inner for loop. So once we fix that, we got this answer. And again, we can fix the problem of the length of these decimal numbers by simply adding a round function. So yeah, but otherwise the Cartesian product function is working fine. I will just show you once, just in case. Number two, number two. Okay, so after adding the round function, this is the result that you will get. Now, let's look at the final function that we have to implement, which is max-min composition. So let's now start with max-min composition. So define max underscore min, pass the relations R and S, which are global, like here. And now, since R and S here are in 2D arrays, we want them as a 1D array of 16 elements. So we will simply convert them using the NP array operation. Sorry. And similarly, the same thing for S. Once we are done with that, we will initialize the output variable. So let's say temp and np dot zeros. Now here we need to specify the dimension. Okay. Now here we want to specify the dimension. If you remember the explanation, so now to define the dimension, we have to remember that the output variable will take the first dimension of first relation and second dimension of second relation. So r dot shape 0, comma s dot shape 1. Okay. Now let's also introduce a temporary variable t, which will be used to store intermediate values. Let's iterate through all the elements in RNS. For I in range of length of R. Okay. Sorry, I accidentally ran the cell. Sorry, I accidentally ran the cell. Okay, so after that, for J in range of length of S and for K in range of length of S. Here in this particular case, the R and S positions won't matter because all the relations have same dimensions. But in other cases, you need to remember where we are putting R and where we are putting S. So after these three for loops, we need to collect intermediate values, right? So we work on first row of R relation or the first relation and first column of second relation. So here we will collect the value in this temporary variable t minimum of R of I, K, and S of I, sorry, S of K, J, if I'm not wrong. Okay, once we are done, ही लाईन परत घे, मी खूप फंबल करत होते. Okay, परत. So now let's store the information in this temporary variable t. Minimum of R of I of K, comma, S of K, J. So here we are taking first element from first relation and first element from second relation, and then we will go row wise for first relation and column wise for second relation. Once we have collected all the values, the minimum values for that particular row and column, now we will select the maximum of all these. So m of I, j is equal to max of t. This is pretty much similar to the matrix multiplication function that we used to write in second year, I think. So once we have taken the maximum value from variable t, we will simply clear it for the next round. And once we have iterated through all the for loops, simply print this temp variable and we will get the maximum composition for R and S fuzzy relations. Okay, nothing happened. Oh yeah, I have to call this function max underscore min past R and S. What is happening? Oh, okay. Fine. Oh no. Okay. So this is the maximum composition. If we compare it, this is R and this is S. So we can see, okay, let me pretty print R and S so that R and S here, so that it will be easier for us to read. So, okay. So now I'm printing R, S and the output. So it will be easier for us to compare. So, okay. So let's just check the first line of R and first column of S. Okay, so they are both 0.3 and zero point 0.1 only. So we are not going to get any different values. So let's check last row of R and let's say last column of S, right? So if we check the first value, zero point 0.6 and 0.7, 0.6 is minimum. For second one, 0.6, 0.6, both are same. For third one, 0.5, 0.5, both are same. And for fourth one, 0.3 and 0.4, zero point 0.3 is minimum. So now we have 0.6, 0.6, 0.5 and zero point 0.3. Now we have to select the maximum of those, which is 0.6. So if we look at the last element in this composition, it is 0.6, which means our maximum composition is working correctly. So we have implemented LP4 SUA first assignment successfully. Now let's get back to the presentation. The last part of the video is Fiverr Questions. Here we will discuss what kind of questions can be asked regarding this assignment in your practical exams. We have already covered some of the questions like what is fuzzy set, what is fuzzy logic, what is a membership function, and the difference between fuzzy set and a crisp set. Now, let's look at what are advantages and disadvantages of a fuzzy set. So the advantage of fuzzy set is that it can work with noisy inputs. So here we don't need to provide precise values. We can give approximate values or ambiguous values and it will still make it work. Second advantage of fuzzy set is the construction of fuzzy logic is easy and understandable. As we have seen, the code was very easy, the explanation was very easy. So obviously the construction is very easy and understandable. Next one is it provides a very efficient solution to complex problems as it resembles human reasoning and decision making. So going back to the first example, if I want to select a group of funny people, it is not as simple as saying people with good sense of humor and bad sense of humor, because sense of humor is an entity which has various degrees, just like fuzzy sets which has multiple degrees of membership. So the last advantage of fuzzy set is that it works well with little data, so which in turn will help in saving memory. Now let's look at the disadvantages. Since the data is very vague and it is not precise, there is no systematic approach to solve a given problem through fuzzy logic. Proof of its characteristic is difficult or impossible in most cases. Because the data is ambiguous or vague or it is not precise, proof of its characteristics becomes difficult. So, next point is as fuzzy logic works on precise as well as imprecise data, most of the time accuracy is compromised. Okay, now let's look at some of the applications of fuzzy sets. One application would be altitude control in spacecrafts and satellites, automotive system for speed control and traffic control, decision making support system, chemical industry for controlling the pH, drying, chemical distillation process, etc., natural language processing, modern control system such as expert systems, and neural network. We can observe that mostly fuzzy logic is used in systems where we have continuous values like speed control, traffic control, altitude control, or pH control. So if you remember it like that, it will help you in your Viva. So that's it for today. Thank you.